Alright, first thing I want to tell you is if you want to see the problems worked out completely for section 4.5, go to your Canvas page for the course and click on 4.5 notes part 1. Part 2 is the same thing, but it's short, a couple of pages at the end, so part 1 is all you need. You might need to download it because it's such a large file. It's got like 63 pages of notes in it, but it covers every single problem completely worked out. Alright, so in 4.5 they talk about sketching by using all the information that we can obtain from all our techniques that we've learned so far in calculus. So this is what the author recommends you do. First, check for the domain, intercepts, check for symmetry, possibly periodic, check for asymptotes, horizontal, vertical, slant, find where it's increasing and decreasing. Then you can tell where its local max and mins are. Then find concavity, points of inflection. And I'm not so worried about sketching the graph. I want to see if you can find the information. Alright, so this is how I broke it down. Domain. So you look where a fraction is dividing by 0. Or for an even root, you force it to be greater than or equal to 0. And for logarithms, it's greater than 0. And for different trig functions, you've got different domains, including the inverse trig functions. You've got the intercepts, x and y intercepts. You get symmetry, even and odd, or periodic. You got your vertical. Remember, your vertical is typically where your denominator equals 0. And to show you have a vertical, you have to take the limit as x approaches that number from one side or the other. For horizontal, you can just say if the top is 1 degree larger than the bottom, it's not going to have a horizontal, but it will have a slant. If the top is the same degree as the bottom, it's leading coefficient over leading coefficient. If the top is smaller than the bottom, it's going to be the x-axis, y equals 0. Take the first derivative to find decreasing and increasing. Divide it up, number line, check intervals, values in each interval. And that way you can know where it's increasing and decreasing. You can find local max and mins that way as well. And then concavity, take the second derivative, and now you're going to find out where it's concave up and down. And if there's a sign change, as long as it's in your domain, that is an inflection point. So let's look at a few problems here. I think there's 6 examples in the book. First one, your domain is everything but -1 and 1 because you're dividing by 0 there. You find your x and y intercepts. This one is even. Plug in the negative x into the function, you get back the original function. It does have a horizontal asymptote, and you find that by going off to infinity. And you actually invoke L'Hopital's rule there. Vertical, it's where the denominator equals 0, and there's 2 of them, plus and minus 1. First derivative, simplify it. It says equal to 0. Find where it's 0 or undefined, divide it per number line, and you find where it's increasing and decreasing, and then you can tell where you have a local max here, but nothing else on the other 2 points. Concavity, take the second derivative, simplify it down, set it equal to 0, divide it per number line, test regions, and now you know where it's concave up, concave down, concave up. And you don't have inflection points here because these points are not in the original domain. Your domain for this one is greater than -1. Your intercepts are what they are there. It doesn't have symmetry, doesn't have a horizontal, but it does have a slant. Okay. The first derivative, you take the first derivative and simplify it by multiplying by 2 square root of x, and you get this guy here. And now you can set it equal to 0 and undefined, and you get your values here. Notice this one is a critical number, but it's not in your domain, so you don't consider it. And so you find minus plus, so you have a local min there, and that's it. No local max. Take the second derivative, simplify it down as much as you can, and you find that this guy is always positive no matter what values you pick, so this entire interval is concave up. Number 3, your domain is everything. Your intervals or your intercepts are x equals 0 and y equals 0. It doesn't have symmetry. It has a horizontal at y equals 1. It doesn't have a vertical. When you take the first derivative and set it equal to 0, you get one critical number, and you find decreasing, increasing, so there's a min there at -1. You can take the second derivative and factor it, you get -2 as your only critical number, so you know it's concave down and then concave up. and you do have an inflection point there. Example 4, 2 plus sine x does not equal 0. It's always positive no matter what, so your domain is everything. Your intercepts, you find your x and y intercepts. There's no symmetry, even or odd, but there is periodic symmetry every 2 pi. No asymptotes. Take the first derivative, set it equal to 0, and you find on the interval from 0 to 2 pi, you got two points that are critical values, and so you check in each region and you find it's decreasing, increasing, and decreasing. So you have a local min there and a local max there. Take the second derivative and simplify it down, and you get your critical values here. And so now you know it's concave down, concave up, concave down, and you got your inflection points. Then number 5, you're forcing this to be greater than 0. So when you solve this, you find that x has to be between -2 and 2. Your intercepts, you find those as well. You can do that. Symmetry, it's symmetric about the y-axis because it's an even function. Vertical asymptotes at 2 and -2, the endpoints. No horizontals. When you take the first derivative and set it equal to 0, you get plus or minus 2, which are the endpoints, but you also get 0. And so you got increasing and decreasing, so you got a max there at 0, which is what I just said right there. Take the second derivative, simplifies down to this, divide up your number line. There are no critical numbers between -2 and 2, so you check the entire interval and it's negative, so this is forever concave down. And your graph confirms that, concave down over the entire region. Now slant asymptotes, in order to find those, you have to do long division. So a slant will only occur when the top is 1 degree larger than the bottom. And when you do your long division, you will always get a line. So remember to show every spot when you're doing your long division, and you say x times what gives me x squared? Well, it's x. So now x times x is x squared, x times 1 is 1x, and now you subtract. And you get this, and now x times what gives you -1? Well, it's -1. So now -1 times each one gives you this, and then you subtract, and you throw out your remainder. You don't care about your remainder. And you do the same thing with these two as well, and you get y equals x minus 1, y equals 4x plus 2, and y equals 2x minus 3. Example 6 does have a slant. So your domain here is everything. Your intercepts are just the origin, 0, 0. It's symmetric about the origin because you plug in minus x into the function, you get negative of the original function. It doesn't have horizontals or vertical asymptotes, but it does have a slant. If you do long division, you get y equals x when you throw out your remainder. Alright, so take the first derivative, set it equal to 0, you divide up your number line, and it's forever increasing over the whole interval. And it doesn't have any local max or mins because there's no sign change on the first derivative. Now you take the second derivative and simplify it. It takes quite a bit of work. And then you set it equal to 0 or undefined, and you get 3 critical values at -√3, +√3, and 0. So you got concave up, concave down, concave up, concave down, and all 3 are inflection points. And so if you look at this, here's your slant asymptote, and the graph actually traverses it. It crosses your asymptote, which is rare, but it gets infinitely close to the asymptote from above, and here it gets infinitely close to the asymptote from below. And that's what a slant will do. Just like all our asymptotes, they are like magnets to the function.